Hey everybody. We are continuing our discussion of section 2. So we're on to subsection 2, increasing and decreasing functions or intervals on which functions are increasing or decreasing. So our one learning objective, which is not essential, but that's fine, who am I to judge? It's still good, is to identify a function as increasing, decreasing, or constant on an interval. And with the little caveat that we'll try to do this from a graph, it turns out it's a little bit harder to do it by definition from a formula, but whatever, we'll manage. Okay, graph below shows two interesting but gross sets of information. We have the total amount of solid waste generated, so trash basically, generated in the United States. These are the triangles graphed over time here. And then the per capita, so the amount per person of solid waste. So total amount of waste is triangles, and then the squares here is per person. So the squares use this axis on the right to measure, so per capita trash generation. So it's measured in pounds per person per day, and then just the total amount is in millions of tons. So, man, yikes. Okay, our questions. First, what is the average rate of change in total waste generated between 1990 and 2000? Okay, so we've got a specific window to look at. We're looking between 1990 and 2000. And we're looking at total waste, which narrows it down to, I believe, the triangles. So 1990. So this is more like the graphs you see common in popular science and not so much in math, because the 1990s should have its own little, delineating line, a little grid mark there. But instead they put it right in the middle because whatever, fine, we'll cope. So that is measured on the left axis, which is also a common thing. Sometimes they'll measure things differently on the left and right axes. And let me see if I can actually get that at the height that we want. So something like that. Again, it's telling us what that number is, so we don't really have to guess, although 208.3 does look feasible from that. So in 1990, 208.3, what is that, million tons of solid waste. Delicious. And then 2000 is our comparator year, so we're going up from 2000. And again, our height is something like that, but we're spared having to approximate from this picture because they give us a numerical value. So that's all interesting, but unless we actually knew how to compute this, knowing those 2 points is not really enough. So average rate of change, and this is from 1990 to 2000. And in this case, I actually am going to say we don't have function names for this, but maybe we could call this like total waste or something instead of per capita. This will just help remind me that what we're looking at is not the squares, it is the triangles. And so this is basically total waste at 2000 minus total waste at 1990. This is our B and our A, if you will, in our average rate of change formula. And then we're looking at the difference between those two values. So maybe just off to the side, we can remind ourselves from the previous section, previous subsection, average rate of change in general of some function looks like f of b minus f of a, and then b minus a on bottom. So our a in this case is 1990, our b is 2000. And usually we'd have to, well, not usually, previously we would have some formula, we would plug in 2000, plug in 1990. We don't actually have to do that here. The graph does all the work because the output, whatever total waste of 1990 or total waste of 2000, is just the output, the height of this triangle here. So in 2000, the height was 242.5. In 1990, the height was 208.3. So those are our two outputs. Those are the two things in the numerator. I've already forgotten. Got the memory of a goldfish. Actually, I heard that that's the myth, that goldfish actually have pretty decent memory. I'm sure you'll flame me in the comments if I'm wrong about either of those things. And then difference between those on bottom might as well. We've got the moment to simplify, so let's do it. And then I think if we do that calculation, this is 34 and some change divided by 10, so we're looking at 3.42. And then here's a great moment to think about units. Said no one ever. But the thing on top looks like something to do with total waste. So this is in millions of tons. And then on bottom, this is a difference between 2 years. And so ultimately, the units on this get divided as well. So this is million tons per, which is a nice way of saying division, million tons per year. I love moments like this where the arithmetic or the algebra, the stuff that we've set up that we're doing with the math, also helps us with the interpretation. Because if you just think about units on this, average rate of change feels like it could be almost anything. But if you just follow the actual operations, we took a number on top, we divided it by a number on bottom, and so because the units are attached to these numbers too, those units get divided as well. So while we were doing these number calculations with our calculator, whatever, in the background, this unit division was also happening. So our interpretation of this in context is something like we see from 1990 to 2000 that the total amount of waste generated went up by at a rate of about 3.42 million tons every year. And so that's basically saying from that triangle to that triangle, every year that went by, it kind of, on average, inched its way up 3.5-ish million tons. So that's, that's not good. But it does seem to be a representation of this trend. It doesn't really account for any of the stuff that happens in between, like it was kind of slower here and then faster here. This is just kind of the average over that 10-year time period. Okay, same thing, but now what is the average rate of change in per capita wastes? And then for fun, we'll pick different years to work with. I will also pick a different color to work with. So our graph's going to be kind of crazy no matter what, but we can do our best to avoid it, I suppose. So we're looking at average rate of change. It's still same starting point, still 1990, but now we're going up to 2010, I guess just to keep things exciting. And then, so it's per capita waste, so maybe I'll write PCW instead, just to differentiate it between this total waste calculation we did up above. So this is like per capita waste at 2010 minus per capita waste at 1990. Oh, it's like every video I find something that looks like something it's not supposed to. So now I've got capital C and parentheses that look too much alike. We've run into 5s that look like S's. We've got T's that look like pluses. I am a mess. 2010 minus 1990. So this is just our average rate of change calculation. Here are inputs getting subtracted. And just like part A, we have no formula to plug stuff into, but that's fine actually. The graph does a great job for us. So I got to remember my years. So here we're looking at 1990 again, but instead of going all the way up to the triangles, we're just going up to the squares there. And this one uses the horizontal, the right axis here, get my directions straight, to gauge stuff. So per capita waste generation is measured over here. So that 4.57 should be our output, and yeah, it looks like more than halfway toward that 5, so sure, why not? And then in 2010, slightly less cluttered, but there's our data point there. Not too different, 4.43 and 4.57. All right. So when we go back, we'll actually use those outputs. I got to make sure they go in the right order too. So this is 4.43 and 4.57 was our starting point. The direction of these is important. So making sure I get the 2010 data point reflected first, and then the 1990 reflected second. The difference between those is 20. And this time we get a negative number. I think with some quick scientific calculation, we end up with negative 0.007. Now, the units on this are a little wild. I would argue they still make sense, so bear with me, but this is what word problems are all about, right? This problem's about trash, and now you feel like the way I wrote it was trash too. So this numerator thing is in, let's go back up to our units here. On the right side, pounds per person per day. Great. Pounds per person per day. So how much each person generates on an average day. And then in the denominator, it's the units of years. So not only do we get the crazy unit of pounds per person per day, we get pounds per person per day per year. So our crazy unit of measure gets even crazier. But again, I'll try to make the argument that while there's a lot going on here, it still makes some sense. So this is saying that the rate at which everybody generates trash in a given day is actually decreasing by about 0.007 pounds every year that goes by. So every year that goes by, each person is generating less trash, which I think is backed up by this picture. Now, the drop-off from 4.57 to 4.43 is not super dramatic, but it is a decline. And it's kind of wild because it happens at the same time that total waste was, for the most part, rising. So per capita waste went down, total waste went up. So that's an interesting thing. So one thing that average rate of change captures well is that whenever it's negative, that's implying for us a decrease. I need to, surprisingly I haven't used black yet. So there we go. So this negative means that what we're seeing is a decrease on average. I feel like I'm using the word average way too many times. Average rate of change. So that's right, a decrease in per capita use as the years go by. Okay, so last question for this one. During what 5-year period was the average rate of change in total waste? So going back to the first one, total waste. When was this average rate of change largest? When was it smallest? Okay, so going back to total waste, which was our triangles. Man, you're going to be so glad we're not talking about garbage anymore. That's how I'll make you excited about math. I give you the garbage example, and then anything else we give from that point forward feels like it's just delightful. Okay, so last thing to do with this garbage problem, and I already forgot the question. Great. 5-year period where average rate of change was biggest, and 5-year period where it's smallest. So 5-year period sounds arbitrary until you remember that the graph only comes in 5-year segments. So that's kind of the smallest that we can work with, since that's how frequently this thing was measured. So, all right, we're looking for largest average rate of change. And since average rate of change if we're only looking at 5-year segments, the width of each of these, the denominator of that average rate of change calculation is the same for all of them. So really, we're looking for the biggest jump. Although in general, you'd be looking for the steepest line, essentially, because the steeper that line is, the greater that average rate of change is supposed to be. So, these are uphill, so certainly steep, but I think if I'm comparing, this one so far looks like it's the steepest, and I don't know that any of these other ones are gonna put it out of the competition. So I think over a 5-year period, this looks like it's the biggest jump. So let's record that. Largest looks like it's going to be from 1985 to 1990, which I don't know. Thinking back to the late 80s, was there lack of recognition of trash? Yeah, probably. Okay, maybe that tracks. And then smallest. And maybe let's make a quick note just for the sake of posterity here that what we were looking for was basically the steepest growth. So the segment that kind of rose most rapidly there. And then for the smallest, this is going to be the opposite end of the spectrum. So English is not great. Like steep is a great way to say how vertical this thing is. I don't know if there's a perfect analogy for how not steep it is. So this could be sort of shallowest, or even a decline. Because remember, we just saw average rates of change can be negative. So if you really want small numbers, gosh, negative numbers are the way to go. They're as small as you can get. So if we're looking for, we'd look for either growth that's just barely, but if we're looking technically for smaller numbers, we could go negative. So we're still thinking about the total waste here. These are pretty, that gets pretty shallow, so that maybe we'll keep that one in mind because it's steeper there, looks steeper there. This is the steepest one, so that's not going to be it. That one could put it, I don't know, that's pretty close. That's steeper again. But actually, it almost feels like cheating, but this last one is going to take the cake no matter what. Because this is the only time where total waste went down. And since more negative number is going to be smaller than any of these other positive growths here, that last little segment is definitely going to win. So from 2005 to 2010 was the only time we saw a decrease. So that's definitely going to be the smallest average rate of change by virtue of being negative to a certain amount. Okay. So what this is kind of leading us toward thinking about average rate of change, it's not a perfect analogy, but when we think about moving uphill, we go from one point to another. If there is no point where you sort of dip back down again, then we say we are strictly increasing. So this is a very kind of complicated definition to capture this, but that what I just said is kind of the heart and soul of it. So you're strictly increasing on some interval if whenever you pick points on that interval, the one that's to the right is higher up. So no matter which ones you pick, if you're on some interval, no matter how far apart they are, and the one on the right is higher by however much than the one on the left, then you've got yourself an increasing function. I just realized I'm doing mirror image, and that's probably going to flip for you. Sorry. So the same thing goes for decreasing. If you have the point on the left is always lower than the point on the right, then that's going to be decreasing on that interval. And so here is a written record of that, if you like. I told you we were going to get away from the trash example, and I forgot I made use of it again. So I am not to be trusted. I'm sorry. So P of t, we're giving function names to these things now. So there's our per capita waste, and we're going to ask on what intervals is it increasing, decreasing, or constant. So constant is where it just stays flat for any amount of time. So back to per capita waste. So those are our squares here. And all right, we started our lowest interval. We're immediately headed uphill. So let's start at 1960 and let's just keep counting until we stop going uphill. So for increasing, and then it stops there because it stays flat between 1970 and 1995. So let's start cataloging this stuff. They've got spaces left for us for increasing, decreasing, constant. And so let's start doing that. So is the same as 1960. So what I kind of want to write here is 1960 to 1970, and I actually tripped myself up the first time. But in actuality, what we've got here is from 1960 to 1970 is the same as t equals 0 to t equals 10. I'm also going to try to be responsible about parentheses here. So this is an interval. But it turns out that that increasing at a point is sort of a difficult thing to keep track of. So the most responsible thing when we talk about these intervals of increasing, decreasing, and constant for a function is to just use those parentheses rather than the square brackets to include. You can kind of get away with it either way, but I think the most responsible option is to use the parentheses with this. So let's see where else we're increasing, decreasing, etc. So we made our way from 1960 to 1970, and then it goes flat. So let's catalog that. Let's make sure we track that as being a time when this function is constant. And because that's that increasing, we're looking for uphill to the right. Constant, we just ran into totally flat. So that we're going to track that too. 1970 is the same as t equals 10. And 1975 is t equals 15. Again, we're just using this same definition for that input variable. What happens after 1975? We're headed back uphill again for a while, uphill, 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 and then we stop at 1990. So 1975 to 1990. We are back headed uphill. I'm leaving a little space here for 1990. Gosh, that's 30 years after 1960. So I'm just trying to do this translation here. At 1990, it started to head downhill, if I recall correctly. Yep, there it is. So 1990 to 95, we have this little tick down in per capita waste. So not as many not as much waste per person for that brief 5-year span. So that's our first decreasing interval because we're headed down to the right. So now we're looking at between 30, t equals 30 and t equals 35. Again, that would be 1990 to 1995. We're headed downhill. Where else do we have? We have a brief little tick back up and then downhill for the rest of our domain. So increasing between 1995 and 2000, and then decreasing from 2000 until 2010. Okay, so increasing again, and then decreasing for the last part of our domain. So from 2000, which is 40 years after 1960, to 2010, which is 50 years after 1960. Whew. Okay, so 3 intervals of increase, 2 of decrease, and 1 where it's constant. So it turns out the most responsible way for me to, most responsible kind of separation here is commas. And I know since you've probably spent a lot of time writing domains of functions and you've been using those fancy little union U's potentially, depending on how mean your teacher is, like this guy, you've been doing a lot of those problems. So the comma may come as a little bit of a surprise, but it turns out if we're being completely responsible, then we're not saying that it's increasing on the union of all those intervals actually squished together. It's just increasing on one interval, on another, and on another. So we just separate those with commas like we would for any other list. A couple of other remarks about this. So one of the things that's challenging about these intervals is the thing you end up with, it kind of looks like a point, right? This could be mistaken as like an x comma y, 0 comma 10 situation. But it turns out that the things that we're cataloging here are always real values of our input. So these are intervals of t value. And maybe that's important enough that I want to kind of make a written remark about this. So all of these things, these are intervals, first of all, to remind myself that they are not, in fact, points, and that they are intervals that consist of the input values for our function. And the reason that's important is they're not points. They actually don't refer to the output of this function at all. And one way you can kind of track that and make sense of it is maybe that the increasing, decreasing, and constant component of this is already telling us what the outputs are doing. It's already saying go uphill or go downhill or stay flat. It's just our job to say, where does that happen in this function? And that's what input variables are all about. They tell us where the address is that we can find that behavior in the output. So again, I tried to be careful about the phrasing of this on what interval or intervals of t values. And so again, that's exactly what we are actually coming up with here, intervals of t values. Okay, so depending on how sensitive your homework system is, it may be more or less important to write parentheses and not square brackets. It may be more or less important to write commas here, but it will always be important to remember that these are intervals of that input. So there's increasing, decreasing, and constant, and we'll be back to talk about one of the more important types of functions in our family of functions next time.